I'm Hope, KM4IPF, and I'm here with Jerry, N0JY. And right here are the two satellites, Fox-1D and Fox-1 Cliff. And they're the ones getting ready to go up in space. What can you tell me about this?
Well, Hope, what we have here are two of our latest CubeSats. On your side is Fox-1D, and over here is Fox-1 Cliff. These are amateur radio CubeSats that will receive and repeat your amateur radio signals, as you're familiar with. And they also carry experiments for various universities that we fly and bring back telemetry and experiment data from them. Both of these will have a camera in them as well, so that we can take pictures of Earth through this hole here, and you'll be able to download on your ham radio receiver pictures of Earth as the satellite passes. There are 10 circuit boards inside there that are stacked up that provide, well, if you start from the bottom, which I have pointing up here, kind of like these. These are actually the ones that go on the sides, and Bob brought these in to demonstrate the antennas, how the antennas are put on, so that you could see what one looks like when it's extended, because on these they are coiled up because that's the configuration they have to be in when we test them in the chambers here at Florida. So he brought those to demonstrate what they look like when they come off of the satellite and what the antenna looks like when it's deployed. But circuit boards similar to that one are all stacked up inside there, and they have your transmitter, your receiver, your IHU, which is our computer that runs the spacecraft, and then a power supply, and it's got a battery board with some fairly big A cells on it. There's 6 A cells. Then at the top of the satellite, which again this is upside down, but at the plus Z end we call it, there are 2 experiments from the University of Iowa and Fox-1D here that will map the Van Allen radiation belts. Then there's an experiment from Virginia Tech that's a camera that will take pictures of Earth, and at the very top is our L-band down converter. You know that AO85 Fox-1A had the UHF and UHF up and VHF down for your radio. These will both also have the capability of receiving on 23 centimeters, which is known as L-band, and then transmitting back down, repeating on 2 meters. So we'll be able to have 2 options for uplink on both of these satellites to add a new challenge and some new fun for the hams.
Oh, and also, I want to ask why I'm wearing this.
You're wearing that. That's what's known as an anti-static wrist strap, or ESD for electrostatic discharge. The satellites are very sensitive, the electronics are, to any static electricity, just like a lot of electronics are, but these are even more sensitive than typically what you find on Earth. So the mat here that your hand is on is an anti-static mat. The wrist strap that you're wearing keeps you from building up a charge from walking on the carpet or something. And then if you were to touch the satellite and get that spark that you get when you get static electricity, that could damage what's inside the satellite. So we take lots of precautions to make sure that we do not destroy the satellite before we ever get it launched.
Oh, so when it does come back down to Earth, when it's not usable, would it like burn up if it like slams on the ground? Would it kind of catch on fire or just fall to pieces?
Actually, we have to make sure that if it does, or when it does re-enter, that none or very little of it will ever make it to the Earth, because that poses a threat to you or me or anyone walking outside, for example. When it comes down from the sky, if it stayed intact, or even portions of it that are traveling at several thousand miles per hour, that could injure or kill you. So as part of our ability to even be launched, we have to satisfy a few government agencies that when it does re-enter, none of it will make it back to Earth and pose a threat to anyone.
Yeah, you don't want anyone getting hurt, because that could be bad.
That could be bad.
So why is there some sort of tinfoil looking thing on it?
The tinfoil that you see there covers a hole that's identical to the hole here. The hole is there so that the camera can look through and take pictures. Because this panel and this panel are identical circuit boards, we can use them interchangeably. So we put an infrared filter on the end that has the camera, and we cover that hole on the end that doesn't have a camera to prevent any thermal leakage, to prevent warm air from getting out or cold air from getting into the satellite. Cold, not air, but cold from space.
Yeah, like when it goes away from the sun on orbiting the Earth, it might get real cold, so you don't want any cold getting in, and you don't want heat getting out at that point.
Exactly, because the electronics inside like to perform at a comfortable temperature, cooler than what it is in the room here, but they don't want to be extremely hot or extremely cold because it changes their performance and could damage them. So the idea is to keep the satellite at a comfortable temperature so that everything operates happily.
Well, I've checked on Fox-1A, and I only got into it twice. Texas and somewhere else. What do you think went wrong that it broke on the launch or something?
If you talk to Texas, you don't need to talk to anybody else. What went wrong with the satellite, what we believe went wrong, was that the receive antenna, which you see here on Fox-1 Cliff, it had a problem where the antenna attaches to the satellite. And that caused an impedance change to the antenna. And as you know from your ham radio, for an antenna to function efficiently, it needs to match a certain impedance for its frequency. We wound up with a large impedance change, which basically caused the antenna to be detuned and therefore not hear as well on 435.180 megahertz. And that's why it is harder in hearing you, and you might need more power to reach it than we originally had intended. Knowing what we do from that, we've made changes with Fox-1 Cliff and D to ensure that these connections are not going to cause that same type of problem, and we spent extra time tuning and checking the antennas very carefully to make sure they're as sensitive as they can be.
It looks like that one is soldered onto the antenna, or onto the satellite. Is that like where it connects and there was something wrong with the solder?
Well, exactly. The solder that was originally produced to hold the antenna on did not grab the antenna properly, and the antenna actually came out of the solder when we were preparing it for flight.
I've made antennas. I know how that works.
So you got it. So what we did, because we had very little time left before we had to deliver the satellite, we made a fix to it that was a less than desirable fix, which would be to take it apart and resolder it the original way, and used some conductive solder, conductive epoxy, to hold it on, essentially kind of gluing it on, if you will. And that is what we believe added some of the extra capacitance to it, because it made that connection, which is very tiny here, as you see, with the solder, into a bigger area. And that's part of what detuned the antenna. So they are soldered directly onto it. They have one little piece of wire that also loops over them to help hold it down to the board.
Okay, and when the fishing line melts, does it melt because it's plastic? And when it melts, would it damage the satellite if it melts and actually goes on? Or would it float away because it's space?
Well, there's two answers to that. First, when the fishing line melts, the only thing that's in contact with it is the resistor that causes it to melt. So there may be a little bit of residual fishing line on the resistor, but it is not heated over a large enough area for it to drip like a candle or something, you know, onto other parts of the satellite. And then as far as things floating off into space, the fishing line has to be, this is another one of the orbital debris requirements, has to be fastened such that it can't float off into space once it has broken. So a little piece of it will remain around the resistor there, tied to this post, and the rest of it will remain hanging off the end of the antenna. And actually in our tests, and you may be able to see when it's on orbit, that when this antenna deploys and it's sticking out here, that little piece of fishing line, of course there's no gravity in space, so whichever way it decides to go, we have seen it show up in the camera pictures. So you might be able to see that little piece that's remaining when it does get in orbit and start taking pictures.
Okay, and this is kind of more of the space station, but for the space station, when they send slow scan television, would the signal maybe accidentally or would it purposely go through the satellites?
No, that could happen if it were prearranged, but their frequency is far enough different than ours that we're not going to pick it up and relay it. We could, because they use FM, if our receive frequency was the same as their transmit frequency. Space station transmits on 2 meters for their slow scan TV. We receive on 70 centimeters, 435 megahertz, so we're not going to hear that signal anyway.
Well, if that receives on it, then how come my satellite station transmits on 2 meters?
Actually, you are transmitting on 70 centimeters. You know, you have a dual band HT, correct? So that you're listening to the satellite and your display is probably showing 2 meters, but you're actually transmitting on 70 centimeters. For both, at least in the case of the Fox series satellites. There are other satellites that you uplink on 2 meters and downlink on 70 centimeters.
Okay, I just realized that I was actually talking about SO50, and right now we're talking about a different kind of satellite. I've only talked on it twice. Well, I've actually talked on it more, but only made 2 contacts from it, 2 different times.
Hopefully you'll have a lot more chances very soon when these go into orbit, because they will be similar to AL-85. So you can use your same equipment and make a lot more contacts.
Okay. Also, about the changing or different colors, this one is kind of brighter sided than this one.
In order to help keep the satellite evenly, at an even temperature, we spin the satellite very slowly around the z-axis.
So that's why I have to turn my antenna for the polarity?
No, that doesn't affect it as much as the way where the satellite is in relation to where you are, as far as its orbit. This can cause some slow fading, depending on where that is. Because if you imagine this receive antenna, which is on the entire satellite, and say you were at Earth down here, when the thing is rotating around that z-axis, now you've got perhaps the satellite blocking part of that antenna from where you are until it rotates back towards you. That's probably not going to cause a polarity change, but it could cause some fading on your signal. And you mentioned the colors. In order to impart the spin, we use what is known as photon drive. And essentially, you'll notice here that there's more gold on this side of this solar panel than there is on this side. So when the sunlight hits it, the sunlight is reflected more by the gold and absorbed more by the darker side. So that causes a little push on the satellite, which in space there's really no resistance other than its mass, so it will start to turn slowly around its axis.
Okay, and 2 more questions I have thought of right now. Well, if there is a rocket coming up, what if those are in orbit right next to where it comes and it gets bounced off?
You're talking about the rocket that goes up might hit it, or the same rocket that's launching it?
If there's any different rocket or something going up with it, like this is the satellite, this is the rocket, what if this happened?
They being the people that launch the rockets and that provide us a ride to our orbit, do a lot of specific planning about where we are in orbit, where their rocket is going, and all of the objects that are orbiting Earth that are a CubeSat size or bigger. They know where they are all the time. Therefore, they make sure that they plan that that isn't going to happen. Because if they were to collide in space and one breaks apart into smaller pieces, then they can't see those smaller pieces with radar, and you have all this debris floating around, which could, like a domino effect, start hitting other satellites and other rockets and just turn into a big mess. So they do a lot of planning to make sure that doesn't happen.
Like if there's a bunch of satellites like my fingers, and this is the Earth, they all go over here, and then the rocket comes out here when they all just passed. Would that be kind of like how you plan it?
Yes. They're shooting in between them if there's some going around like this, or they're shooting into an orbit that's a little higher or a little lower so that they make sure they don't run into each other.
Okay, and the other question. So who or what would be launching it?
What would be
out of the rocket?
Out of the rocket. Okay, the rocket is a SpaceX rocket, and the rocket has the Sherpa ring on top of it. And then above that is their primary payload. So we're located near the top. but below the primary payload. The whole rocket launches, and then they let the primary payload go into space. They will change the orbit a bit then, just like we talked about, so our satellites don't hit that primary satellite that they just launched. And this ring has all of these quad packs, they're called, around it, with these satellites packed into them, and by timing and direction that that ring is pointing as it's spinning, they let the little CubeSats go all at once. So spaceflight provides that Sherpa ring, and they are the ones that actually deploy our satellites after the primary payload's been deployed.
Okay, so that would be really cool if they all went at about the same time, and you would, like, another satellite might be a little nearby that was already there, and maybe it got some video and it showed a bunch of them coming out. If you were watching the video, that would be so cool.
It would be cool, and I wouldn't be surprised if spaceflight does not video the deployment of the satellites, but I can't say that they would, or whether they would make it public. You know, with the Fox-1A launch, there is a little 3-second video of the satellite coming out of the P-pod, and I posted that on YouTube if you want to look for it. But it's only 3 seconds. They had a camera, and you can see the top of the P-pod open, and then Fox and the other 2 satellites just kind of sailing off into the darkness.
Even though it's only 3 seconds, it sounds really cool.
It is. It just goes by fast.
Do you know what satellite got that video?
It was taken from the rocket itself, where the satellites, they're in a box mounted to the rocket, and they had a camera on the rocket that took a picture of them as they went away.
Oh, like, so it's not, it's probably not on the outside of the rocket, is it?
Yeah, it was on the outside. Have you seen when they launch some CubeSats and such from the space station? They have a camera on the space station, and you see the CubeSats floating away. It's a similar thing.
Yeah, I was thinking of, like, when they have, like, the GoPros or something attached to your helmet, you can get video, but I thought that would melt when the rocket goes up, so I thought, like, on the space station, I've seen a few videos of it going around, but I thought that was from the astronauts that mounted that onto it after it was already up.
I get you, but similar to the fact that they can put our satellite on the rocket and it does not get melted going up, they can put a camera in the same vicinity, and it makes the trip as well.
Well, I guess they need to test those, whatever kind of cameras it is, to make sure it gets bounced like these.
I'm sure that they put them through a lot of testing before they put them up there. We have to do an extensive testing on these to not only guarantee that for our purposes that they're going to be successful when they're deployed, but also to guarantee to the people that are providing the launch for us that we are not going to pose a hazard to their rocket or any of the other satellites. And that's why we're here. Part of the reason that we're here right now in Florida is to subject these to the same types of vibrations that they would see on the rocket launch, and the acceleration forces, as well as to, as we talked about the finger oils earlier, to make sure that they are pure before we deliver them to them. If the satellites have any residue on them from people touching them and such, and that's why I'm wearing these gloves, your finger oils, which you might notice if you have a tablet or something that you use your finger with, eventually you see those little streaks on them, right? So if those get on the satellite, then they pose a problem when you get to space, because they can lift off of it essentially, and you have a bunch of particles floating around that can harm your electronics or get into your camera lens and such like that, or even affect the launch vehicle and other things. So that's part of the test that we have to go through just to be able to launch these, and I'm sure they do the same type of thing to their cameras before they send them up as well.
Okay, and what happens to the rocket after it is done launching these? Does it stay in orbit, or part of it fall back to Earth? I'm guessing not fall back to Earth like these.
There's a couple answers to that, because specifically the SpaceX launch that we're going on, you may be familiar with the fact that their first stage rocket of the Falcon 9, they have been working on and have actually successfully landed it back on Earth so they can use it again. In the past,
we saw that one from the beach around here.
Yeah.
We saw that it landed successfully. A bunch of yays.
There you go. And that's what they're working on. In the past, the rocket would just float through space, and then it would enter the atmosphere and it would burn all up, and they'd have to build a new rocket. So in a particular case of this launch, I suspect that they're going to try to land that stage again and bring it back. There are other portions of the rocket assembly, upper stages, or the Sherpa ring that will be launched from that will stay in orbit for a bit and eventually re-enter.
Okay, and speaking of, well, not speaking of which, because it was a long time ago, but the tinfoil looking thing, is that actually tinfoil or a thing of actual thick kind of metal?
Actually, it's foil tape. So it is a little piece of tape that has foil on one side that is simply taped over that hole, which is the same again as this hole. So it's thin.
So this is actually on its side?
This is laying on its side, so the plus Z, or the top of it as we refer to it on Earth, that's where the camera peeks out so that it can take the pictures. And so again, on the unused side, at the bottom of the satellite, we just put some tape over it.
It sure doesn't look like tape, but as you said, it's foil tape.
There you go. It's just a piece of foil with a sticky side to it.
Right there.
Okay.
At that where this actual antenna connects to it.
Uh-huh.
Well, I see why you have it not actually left out, so you actually have it coiled.
Right.
I see why you have it left out because, or left coiled, because if you wanted to put it right side up, like you have it now, then that would bend the wire, and after making the antennas, we made a quarter wave ground plane. We bent the wires and one of them broke off because of too much bending.
Mm-hmm.
If that gets too much bending, would it like break?
There's a possibility. This wire is called nitinol, and it's very springy, as you see, which is why we can coil it up into a coil such as this one here and store it their way for a month or something, or for however many months before it launches, and it will still spring out to its original vertical or whatever position that it was in. So the antenna itself is pretty flexible, but what we would have to be careful of is pushing it away from the circuit board or something that might cause it to break off where it's soldered on. When we test the satellites, we do have to test them on the air, and then the antennas need to be deployed in order to accomplish that. So we have to carefully set the satellite at the edge of the table to do that, so that the antenna can be extended without, bending it by setting it on the table. So when we do those tests, it'll be hanging over the edge of the table just slightly so that we can have the antenna deployed.
Maybe someone should actually hold it just in case it falls. As you said earlier, it would be a lot of money to have it break.
It would be. Fortunately, with the weight that's in these both weigh just a little over a kilogram, which is 2.5 pounds maybe, they weigh. And so when you have just the edge of it over the table, you've still got most of the mass on the table, so it doesn't tend to want to go anywhere if I do this, for example. That's plenty of room so that the thing hangs over, but it's not going to fall off.
Okay, so how long would it take to get across the world and back to where, like, here? And after that, how many times would you see it during the day?
These satellites will be in what's known as a sun-synchronous orbit, so they will pass over, for example, Florida, twice per day, approximately 12 hours apart. The orbit is 97 minutes, so just a little over an hour and a half, and as you see it go by at, say, 10 in the morning, then it will also come by again at 10 o'clock at night. So you'll see each satellite a minimum of twice per day, and depending on where you are in location to the pass, you of course, maybe get 3 or 4 passes per day.
So if I get 3 or 4, then how many would be descending and how many would be ascending?
Well, basically it's even, so 2 and 2. During the morning, for example, around that 10 o'clock time period, and you know how your orbits are, you say you have one at 8:30 and then another one at 10 o'clock, for example, right? You get a couple of them each time that are about an hour and a half apart. So you would have 2 going north in the morning and then 2 going south in the evening as Florida got over on the other side of the globe, as the Earth turned.
Okay, so like this is the thing, this is the Earth, the Earth turns around. The orbit, I don't know, I can't really make this Earth now.
Make the Earth like that. The satellite is going like this, okay? So the satellite's going around the Earth like this. And where your thumb is Florida, for example, right? So as you go through the afternoon into the evening, you can turn your hand this way, probably easier. You see that now it's coming up over your thumb instead of going down over your thumb as the Earth turns under it. And that's what happens. This is the morning pass, and this was the night pass over here, for example.
That makes kind of sense.
It's
it could make sense to someone who knows more than me.
It makes more sense in a drawing or something, actually, yeah.
So why do you need to do the Doppler shift, and pretty much what is Doppler shift?
Doppler shift is an apparent change in frequency that's caused by the fact that the satellite's moving very fast. It's going some 18,000 miles an hour to orbit the Earth. So as it is coming towards you, if you're familiar with a car or a train going by and how the train whistle will be a higher frequency as it comes towards you, and then after it passes you it becomes a lower frequency, the same thing happens with the satellite. As it's coming towards you, decreasing range, the frequency appears to be higher because the wavefronts are shorter. They're compressed as it's coming towards you. So when it's approaching you, you have to tune your receiver a little higher or your transmitter a little lower to compensate for that. After the satellite passes and it's going away, then the waves appear to become longer because there's a little bit of time in between each one that stretches them out as it moves away. And that's what the Doppler is that you have to compensate with on your radio in order to stay on frequency. When the satellite's directly overhead or at its closest point of approach to you, then the Doppler is 0, but 99.99% of the rest of the time it's changing.
This has been really fun, and thank you for showing me and answering all these questions. Thank you another time? I don't know.
Hope, it's been a lot of fun to be able to share this with you, because what we do with these satellites is for amateur radio, mostly, but there's a lot of educational value and a lot of things that I think it's wonderful that you're giving us an opportunity to share with kids throughout the world a bit of this science and things that they might look forward to doing. So I really had a great time too. Thanks a lot.
I thought I was supposed to tell you thanks.
You did, but I thanked you back.
Okay, you're welcome. So that was a lot of fun. I hope you learned something. This is Hope, KM4IPF. Remember to keep coming to HamRadio.World.